Hello, welcome to this lecture. This is the last lecture of the course, and the last lecture of the course in the reverse chronological ordering that we're going means we've reached the beginning of the universe. So I said in the last lecture we were going to spend the last two lectures looking at the early universe, and so in the last lecture we looked at going from the first fraction of a second all the way out to about 1 billion years or so. And here we're going to look at the universe at timescales about less than 10 to the minus 10 seconds or so. And you might think we've just developed this very successful benchmark model. It tells us a great deal about how the universe evolves. So I plug in my matter density, my radiation density, my cosmological constant density. I evolve those forwards or backwards and I can explain everything. And in many ways I can. And the reason that this earlier period comes into focus is because of some, if you like, fine-tuning problems that exist when you look at them. In other words, when we look at the universe today, there are certain values of physical constants, of parameters that we see, which actually have to be rather fine-tuned. And there's no obvious reason in any of the cosmology that we've seen today that they appear to be so fine-tuned. And some of this is offset. So in the questions at the end of last week, I talked about something called the anthropic principle. And the idea of the anthropic principle is that the universe is how it is just because it is, very simply. In other words, you might say, well, how likely is it that the cosmological constant only takes over now, that freeze-out happened at such a point where you could have hydrogen and helium, that you have fusion in stars, that life evolves. All of these things seem very unlikely. But you're only in a position to ask that question or notice that coincidence if you are in the universe where those parameters exist. So it's very hard to get around the anthropic principle in a certain sense, because if the universe, for example, was wildly different from flat, so for example, if it was incredibly positively curved, it would have just come into existence, reached a maximum size and collapsed again. On the other hand, if it was very negatively curved, everything would have spread out so quickly that you would never have actually formed structures in the first place to go on and form life, etc. And so if the universe didn't have the properties it has, you couldn't be here to ask that question. So all of what I say, in a sense, is offset somewhat by the anthropic principle, but nonetheless fine-tuning, or scenarios where parameters look like they've been fine-tuned, are still things you have to worry about, because if you can remove that fine-tuning and say it's like this because it had to be, it's a much more satisfactory solution. So there are two problems that we're going to look at that force us to go back into this very early universe. And they're not problems which arise there because we can't actually observe that period at all. It's well beyond where our telescopes can peer. But there are things that we observe more locally that still matter. And so the first of these problems is something called the horizon problem. And we've already kind of met the horizon problem in a certain sense. So I think back in the second lecture, I drew a diagram that looked something like this. I had the Earth sitting here, and it has a horizon around it, which is basically as far as light can travel in the age of the universe. And then I noticed that there are galaxies that sit just inside this horizon, and they have their own horizons, of course. Maybe I should just copy and paste these for the sake of it, and let's just change the colour. Oops, don't want to fill, I want to never mind. Let's duplicate that one. There are structures inside this which we see, and their horizons, so this is galaxy A and galaxy B. Then the horizon of galaxy A includes the Earth, it does not include galaxy B. And so here's an interesting thing. If I look at the cosmic microwave background, our favourite thing, it comes back again and again and again. This has the same temperature everywhere. Now that's a surprise. And the reason that's a surprise is because of this reason here. The same temperature is a hallmark of thermal equilibrium. In other words, you turn your heater on in the corner of the room and gradually it heats the room up to the same temperature. But that takes time. Thermal equilibrium must be established. And here's the problem. Galaxy A and Galaxy B cannot send signals to each other. They're outside of each other's horizons. So how come the temperature here is the same as the temperature here? That doesn't make sense. And in fact, it's even more complicated than that, because if you look at the cosmic microwave background, it's got all these little structures in it. We see them here. Lots and lots and lots of them. They're tiny little knots that you can see. And we know that the largest structure in the cosmic microwave background is essentially 0.6 times the speed of light times the age of the universe at the formation of the cosmic microwave background. Because this is the speed of, 0.6 c, because it's not cs. 0.6 c, cs is 0.6 times c. So 0.6 c times the age of the universe at the time of the microwave background. And the horizon, of course, at that sign is simply c times t cmb. And we know that this is about 1 degree on the sky. Because, of course, because the universe has been radiation dominated and been matter dominated, the universe, the scale factor, has not been growing, if you like, at the speed of light. So the horizon grows faster than that. And so, in fact, if this is about 1 degree across, and this is a bit more than 1 degree, but not a lot, there are many thousands of horizons across the cosmic microwave background. And that means even if you imagine that, well, perhaps just by sheer chance, I look out to my left and I see the same temperature as I do if I look out to my right, it's not just a 1 in 2 probability, it's not just a small chance of it being the same, but I've only looked twice, so never mind. There are thousands and thousands of non-causally connected regions in the CMB, and they all have the same temperature. That implies they've all been in thermal equilibrium, even though sending signals between them to establish that thermal equilibrium would have required velocities greater than the speed of light. That is not obviously straightforward. So it's an unsatisfactory scenario in our cosmological model. Why is the universe the same temperature everywhere? Why is it homogeneous and isotropic? No obvious reason why it should be. And that's the horizon problem.